Hi, everyone. Thank you for joining us. We're super excited to be here. And we're going to get started with the question. So I want you to think about the answer and keep it in mind. Are you confident there are no threat actors in your Kubernetes cloud environment? If yes, what gives you this confidence? If no, what actions can you take to address this? My name is Stav. I'm the DevOps tech lead at Mitiga. And when I'm not doing Kubernetes or CI/CD or monitoring, I'm probably sailing. That's like my favorite thing. A funny story is that I actually just got back from a sailing trip in Italy and my flight back got canceled. And I almost didn't make it here today, but luckily I did.
Hi, my name is Ariel, and I'm a security researcher at Mitiga. In my free time, I'm a student in humanities, and my field of research is ancient manuscripts, less cool than Stav.
So today we'll be discussing performing threat hunting in EKS. So let's get started. Just to make sure we're all on the same page, I want to say a few words about Kubernetes. The word Kubernetes comes from ancient Greek, meaning pilot, captain. But in our field, Kubernetes is a platform designed for managing and deploying containers. As virtualization advanced, applications increasingly adopted a microservices approach, leading to a rise in the popularity of containers. Unlike traditional services, containers required more special management, which created the need for a system like Kubernetes to efficiently manage them. Let's say a few words about the advantages of using the Kubernetes ecosystem. As a container orchestrator, Kubernetes offers a range of features, some native to the Kubernetes system and others more relevant when using managed Kubernetes service, such as EKS. Kubernetes provides out-of-the-box scaling and state management, helping to keep applications stable and workload balanced as desired. It also includes native rollouts to ensure zero downtime during updates. Additionally, Kubernetes integrates with AWS to offer external features, such as load balancing via ALBs, storage management using EBS volumes, and other configuration tools. So why should we run Kubernetes in the cloud? Cloud platform provide virtual limitless resources, allowing you to scale your Kubernetes clusters up and down based on demand. Usually when you're just starting small, it's the easy way to go, as there's no need to worry about all the heavy lifting of setting up your Kubernetes components by yourself. And trust me, it's not simple. You don't need to worry about upgrades, patching, and monitoring either, as most of this is done for you as part of the infrastructure the cloud provides. This allows your team to focus on application development and deployment only. So we're going to go over a few important Kubernetes concepts you need to know to be able to sit in this talk. Pods are the smallest and simplest unit in Kubernetes, representing a single instance of a running process in your cluster. These pods operate within namespaces, which are the Kubernetes' way of dividing the cluster resources and creating isolated environment, aiding in your cluster organization. And on the identity and permission sides, Kubernetes implements an RBAC system, role-based access control. In Kubernetes, you can create roles that grant access to various resources across your cluster. Then, role binding are used to associate these roles with specific identity entities. One of the most commonly used identity type in Kubernetes is the service account, which serves as the fundamental identity for granting access to pod. Now that we've set the stage, let's dive into one of the most crucial aspects of performing a cyber investigation: the logs. Generally, the logs are divided into two groups. We have the Kubernetes ecosystem logs and the cloud provider logs, which in our case is AWS. In the Kubernetes ecosystem, we have several log streams that are relevant for a cyber investigation. We have the API server logs that provide insights into cluster operations and API calls, the scheduler and controller manager logs that provide information regarding cluster state and scheduling tactics. The audit log basically records all actions performed on the cluster. And additionally, we have a special log called the authenticator log that provide insights and information of authentication attempts and access requests made to the Kubernetes API server by IAM, AWS's Identity Management Service.
Now, the cloud provider side. The simple way to collect and analyze Kubernetes logs in EKS is CloudWatch, the AWS monitoring service. Regarding the cloud logs, CloudTrail is the AWS audit log. CloudTrail contains records about actions that are made by various types of entities such as users, roles, services, and more. The AWS threat detection service is called GuardDuty. GuardDuty provides alerts of suspicious activity using machine learning and enrichments. Now, we are going to talk about threat hunting in EKS. We'll ensure that everyone is on the same page by briefly discussing what threat hunting is and why it's important. Then we'll perform our own threat hunt together. Sometimes, threat actors succeed in compromising an environment without triggering critical alerts in your threat detection services. We believe you should always assume there are threat actors in your Kubernetes environment and actively search for them. This proactive approach is called threat hunting. Mainly, threat hunting is divided into 3 steps. The first step is to choose a concrete hypothesis, an environment, and a threat actor's motivation. For example, an environment could be your RDS instances in AWS, and the threat actor's motivation could be to exfiltrate all your sensitive data from them. It's important to understand there are a lot of potential hypotheses, and we should choose the most relevant ones for our organization. The second step is to build a list of potential indicators of attack, IOAs, that you can identify in the relevant logs. Threat detection is about quickly flagging potentially harmful activities. Threat hunting, on the other hand, is a more proactive and exploratory process. Hence, it's okay to search for noisy actions as part of that. The third step is to investigate the indicators you found in your environment. Using the context you have on your environment and the puzzle pieces you found, and build the big picture to confirm or disprove the chosen hypothesis. Let's perform a threat hunt together. We have in our example an EKS cluster, of course, and within this cluster, there is a pod with permissions to a sensitive bucket. In our hypothesis, we assume that there is a threat actor that gained persistence to our cluster, and this threat actor is using it as an access enabler to our sensitive bucket. It's important to note that in this hypothesis, we are focusing on the persistence phase and not in the initial access phase. So we assume that the admin user was compromised for a short time somehow, and this is for another threat hunt. Okay, what can be relevant indicators of this attack? In this lecture, we're going to focus on 2 different ways to create persistence to an EKS cluster. The first way is creating persistent access for an external account using access entry. The second way is creating persistent access for an anonymous user from outside. After these 2 ways, we are going to see an example of potential usage of this persistence, and particularly data exfiltration. Let's talk about persistent access creation to an EKS cluster for an external account. In this chapter, we'll see two indicators of attack, one for the access entry creation and one for the connection itself from an external account.
So, as Ariel mentioned, the first indicator of attack focuses on creating persistent access to the cluster. Persistent access means establishing a valid connection to the cluster and being able to authenticate to it. In plain Kubernetes, there are two primary methods of authentication: service accounts managed by Kubernetes and normal plain users. EKS offers out-of-the-box OpenID Connect integration with AWS's identity provider, so we can bind our IAM roles with Kubernetes RBAC permissions through the EKS API. This feature is called Cluster Access Manager. Below, you can see a CLI command of creating an access entry to a Kubernetes cluster, an EKS cluster actually. As you can see, I'm using the AWS CLI and I'm running AWS EKS create access entry. I'm then specifying the cluster name that I want to grant access to, the principal ARN of the role or the user that I want that will be able to log into the cluster. And I'm mentioning the Kubernetes group, which means the RBAC permission within the Kubernetes that I want my role to have. After running this command, the principal that I put in this command will be able to log in and authenticate to the cluster.
Threat actors can use this feature to create persistent access for an external account. We can find this activity in CloudSecNext. We can see here create access entry event name under EKS event source. Under request parameters, we can see the cluster name and also the principal ARN that we want to grant access to. ARN, by the way, stands for Amazon Resource Name. The principal ARN contains an account ID, as you can see in the example. If this account ID doesn't appear in the list of your organization's account IDs, you have a really good reason to suspect that there is a threat actor in your environment. You can build a list of your organization's account IDs with CLI or API. For example, you can use the CLI command, AWS organizations list accounts. However, as investigators, we might not always have the necessary permissions to perform that. So another approach is to compile a list of account IDs based on the log records in CloudSecNext. You can use account ID and recipient account ID fields to perform that. You'll note that the log examples in this lecture don't contain all the fields in the logs, just the most important ones for our needs. After the threat actor created a new access entry that grants their external account access to our cluster, they can connect to our cluster actually whenever they want. Let's see how we can identify these connections in the Kubernetes logs. There are two ways to find connections from external accounts in the logs, in the authenticator log and in the audit log. In the authenticator log, we can see access granted message and also the principal ARN with the external account ID. The advantage of this way regarding connection recognition is the authenticator log actually contains the exact time of the connection, which is, of course, an important piece of information for cyber investigations. In the audit log, we can see every action that the external principal performs in our cluster after the connection. We can see here under canonical ARN, the principal ARN with the external account ID. In this example, we can see a get action. The advantage of this method regarding connection recognition is the audit log contains the threat actor's source IP, which is also important for an investigation, of course. Now, we are going to discuss the creation of persistent access to an EKS cluster for an anonymous user. In this chapter, we'll cover three indicators of attack: enabling public access, granting access to an anonymous user and the actual access itself from an anonymous user. When you create a new cluster in EKS, you can configure access to the Kubernetes API server point. You have three options: private access, public access, and both. Private access means the cluster endpoint is only accessible through the relevant VPC, and public access means the cluster endpoint can be accessed from outside the VPC. The default configuration in EKS, as you can see, for a new cluster is both public and private. Therefore, if you don't need public access to your EKS cluster, make sure to set it to private only. Also, you can configure an allow list of public CIDR blocks to your cluster just if public access is enabled. If someone changes the endpoint access setting or manipulates the allow list of CIDR blocks, this section is logged in CloudTrail. Here you can see update cluster config event name, also under EKS event source. Under request parameters, you can see the current state of API server endpoint configuration, the enablement state of private and public access, and also the allow list of public CIDR blocks. The issue with this log record is the request parameters field, as I described, only shows the current state and not the changes that were made. To address this, we need, of course, the previous state. One way to achieve this is querying the state of our clusters via CLI or API and storing it. Here you can see a simple example to the relevant CLI command, AWS EKS describe cluster, and then the cluster name. But once again, as investigators, we might not always have the necessary permissions to perform that. So another approach is to search past update cluster config events, or even create cluster event for this cluster for the previous state.
So I want to say a few words about anonymous access. Anonymous access in Kubernetes occurs when someone connects to the cluster without authentication at all. Accessing an EKS cluster typically involves using a kubeconfig file, which contains the cluster information, the certificate, and the user configuration. The examples shown demonstrate what a kubeconfig file might look like for an AWS user. Alternatively, if we want to connect to the cluster without specifying a user, we can omit the user section in the kubeconfig file. This results in an anonymous connection. Kubernetes, including EKS, commonly allows some level of anonymous access by default. While this isn't inherently a major security concern, it does mean that RBAC becomes the primary line of defense. A single misconfiguration could lead to a significant risk, especially if your cluster is exposed to the internet. Why isn't anonymous access disabled by default then, on EKS and on Kubernetes in general? It is generally enabled to allow access to the API server for health check or discovery purposes. For example, if we have an application running on pods in a Kubernetes cluster, and we want to put a load balancer, an ALB, in front of them to distribute the traffic, the load balancer needs to make sure its targets are alive, the pods are alive. So it sends health check calls to the cluster to make sure the pods are answering. This is why it needs to have the anonymous access enabled, as our ALB doesn't have an identity. Let's consider an example. A threat actor who gained initial access to the cluster might want to maintain that access using anonymous user. They could create a cluster role that grants access to all the cluster's secret. As we can see in the snippet, the anonymous secret access role is granting get, watch, and list permissions on the secret resources. It also grants permissions to the /API and /API's URL in order for us to be able to query those URLs for the secrets. Then, by using a role binding, they could bind this role with the system unauthenticated group, which also includes the anonymous user. In the third snippet, you can see that after applying the first two YAMLs, the threat actor can access the sensitive secret using anonymous access. I'm running kubectl get secret in the namespace kube system. Then I'm asked to specify a username, and I'm entering a definitely non-existing user and a definitely non-existing password, and I'm still able to log into the cluster and see the super secret.
Let's dive into how we can detect what Stav just demonstrated in the logs. The first indicator of attack is the granting of permissions. This activity is visible in the Kubernetes audit log. We can see here the creation of a cluster role binding that binds the anonymous secret access cluster role to the system unauthenticated group. This binding is a red flag. Also, guard duty generates an alert about that. Anonymous access granted under policy Kubernetes category. The audit log contains Kubernetes data that doesn't appear in guard duty, like response status and stage. But more importantly than that, as investigators, we always prefer to work with the raw logs or the all edge cases. On the flip side, guard duty offers some advantages like IP enrichment and actually built-in logic that simplifies the detection process. The second indicator of attack is the anonymous access itself to our cluster. This activity is also captured in the Kubernetes audit log. For example, here you can see a list action on secrets that performed by an anonymous user, another clear warning sign, of course. Similarly, guard duty generates an alert for this type of activity as well. Successful anonymous access under credential access Kubernetes category. Now, we are going to see an example of potential usage of this persistence, and particularly data exfiltration. A threat actor can use their access to our EKS cluster to exfiltrate data from our sensitive bucket, from the example. But before that, how can a pod in a cluster even access an AWS resource?
When a pod needs to access a third-party service on the cloud provider side, such as Amazon SQS, S3, or RDS, authentication is required. The simplest way to grant access is through access key and secret key, but these are static credentials. Static, also called permanent credentials, are not a secure way of authenticating due to the lack of expiration. AWS and EKS offer API-based authentication with temporary credential use, the most up-to-date method being EKS pod identity. But you also can use the IRSA, IAM roles for service account, which is the previous method, which also work with temporary credential. So basically, if you're still using static credentials, now is the time to make the switch. This is a short diagram explaining how pod identity works. We have a pod that is connected to a service account on the Kubernetes cluster. The service account generates a token. Whenever the pod needs to access the third-party service on the cloud provider side, such as S3 bucket, it sends the token to AWS's metadata servers for validation. Once the token is validated, the temporary credentials are then sent back to the pod for it to use whenever it needs. The key point here is that these credentials are temporary and they expire after a certain amount of time.
Thank you, Stav. Now we understand how a threat actor can use the pod's role to access the sensitive bucket. Now let's see how we can identify this activity in the relevant logs. Unfortunately, there is no trivial smoking gun, as you can guess, but it's a great opportunity to talk about the necessity of anomaly analysis in threat hunting. As we described, in threat hunting, we search for threat actors that succeeded in compromising our environment without triggering critical alerts in our threat detection services. Therefore, it's important to search for them wisely using the context we have about our environment. Here you can see a simple example. This graph is based on CloudSecNext logs. The source entity of the log records is the pod's role, the target entity is the bucket, and the events are access events to a bucket like these you can see here. You can see in this graph a pattern of the application's behavior, but if you take a deeper look, you can see an anomaly between May 12th to May 17th. In threat hunting, we should investigate these events. For example, we need to examine the source IP and the user agent. Also, we should take a look at the event names and consider if we expect to see them in this context, and so on. Maybe it's a false positive, like an admin that just debugging some permissions issue. But maybe not, and threat actor downloaded our sensitive files. Let's summarize our threat hunt. We chose a concrete hypothesis, an EKS cluster with a pod with permissions to a sensitive bucket, and also a concrete threat actor's motivation. We assumed that there is a threat actor that gained persistence to our cluster, and this threat actor is using it as an access enabler to our sensitive bucket. In this hypothesis, we decided to focus on the persistence phase. We built a list of potential indicators of attack, and we understood how we can find them in the relevant logs, both AWS and Kubernetes logs. We discussed how we can identify persistent access creation for an external account using access entry. Also, we saw how we can identify persistent access creation for an anonymous user from outside. And finally, we talked about the necessity of anomaly analysis in threat hunting. Now, what remains is to take the results of the queries and investigate them, build a big picture, and confirm or disprove the chosen hypothesis.
So we're reaching to the end of our talk, and we wanted to conclude it and share some recommendation with you. And we've divided those into two kinds, EKS management recommendations and threat hunting recommendations. So regarding EKS, we recommend you start using Cluster Access Manager. It is now considered the preferred way of managing access, as all access grants are recorded and can later on be logged and traced. Preferably, keep your EKS clusters private, if possible, of course. You don't want to just leave public EKS endpoints open if you don't have to. Switch to using EKS pod identity or IRSA when accessing other AWS resources. Stop using permanent credentials. And regarding threat hunting, make sure you start by enabling and collecting all your relevant logs, your Kubernetes logs, and your cloud provider logs. Start getting to know your logs. Spend some time exploring them and find out what are the relevant fields. And last is, start building your threat hunting strategy. Map out your important clusters, choose the relevant hypothesis, and decide on a schedule to perform it. If there is one key takeaway we want you to take from this talk, is that you should assume there are threat actors in your EKS environments, and you should actively search for them. Thank you very much. We hope you've enjoyed this talk. We have a QR code here for a blog we conducted regarding pod identity, and you have our emails here for questions. And Brian, if there's any other questions.